Hey everyone, welcome to the Chem 1212 Absorption versus Concentration lecture for the lab. Let's go ahead and jump right in. So in Chem 1211, at least in the lab, we learned that atoms are quantized, right? So the same is true for electrons and molecules. Electrons can be in any of various states, and that's what we're calling our orbitals, right? States or orbitals, but can't lie between these energy states. And this should be very familiar from 1211. So at room temps, almost all electrons in a sample are going to be the lowest available energy states. You cannot promote electrons to a higher energy state unless you add kinetic energy or absorption. Kinetic energy is just heat. So you can add it by heat, which is kinetic energy, or by absorption of a quantum of electromagnetic energy, like a photon. Now, the wavelength is going to be represented by lambda. Okay, the wavelength, which is represented by lambda, of the photon required for the transition depends on the difference in energy between the orbitals. Now, this is the formula. Here, this is the same formula we use for the energy lab in Chemistry 1211. Your H is your Planck's constant, 6.626 times 10 to the negative 34 joules per second. And then C is your speed of light, 2.998 times 10 to the 8 meters per second. Now, just a heads up, if you want to use 3.00 times 10 to the 8th meters per second for your speed of light, I'm totally fine with that. Whatever makes life a little bit easier for you, I'm happy with. Okay, so let's remember that the spectra of atoms in the gas phase, like hydrogen or any other gas, have distinct lines in their spectra, okay? Very distinct lines in their spectra. But in solid or liquid interactions between molecules affect the energy states. So because of this, you're going to see a UV visible spectrum of absorption versus wavelength for a solution that shows broad bands, not lines as that you might expect for atoms in the gas phase. Concentration studies are done at the wavelength of strongest absorption at the center of a strong band, and that's going to be referred to as lambda max, okay? A typical spectrum of absorption versus wavelength for fluorescent is shown here, what you're looking at, this actual chart. And the lambda max for fluorescent is around 480 nanometers. This is the instrument you're going to be using in this experiment. It's called a UV visible spectrophotometer. Now, ours might look a little bit different, maybe a little bit more updated, but the idea is the same. It's a big box. You'll pick it up, you'll plug it in, and you'll do that all before we get started. It needs about 15 minutes to warm up, and I'll talk about it if you guys are not comfortable with using the spectrophotometer. We'll talk about it in lab. So the wavelength of light shining through the sample in a cuvette is controlled by the monochromator. Now, it acts like a prism to separate the continuous light emitted by the source into virtually single wavelength light. The intensity of the light after it passes through the sample is recorded by the photodetector. I'm just kind of giving you an idea of what's going on inside of the spectrophotometer. When light passes through a solution, the compounds in the solution can affect the amount of light allowed to pass through it if any of the compounds absorb the wavelengths of light present. On the other hand, if none of the compounds absorb in the wavelength region of the light, then the intensity of the light exiting the solution will be the same as entering. The amount of light that passes through an absorbing solution is proportional to the concentration of the absorbing compound in the solution. Let me say that one more time. The amount of light that passes through an absorbing solution is going to be proportional to the concentration of the absorbing compound in solution. Since the more material in the container to absorb the light, the less light is going to get through. That's what we're getting at here. The relationship is going to be expressed to you by Beer's law. What you see here, your capital A is absorption observed. Your lowercase a is absorptivity of the compound. Your lowercase b is a path length of the light through the solution. And then your C is going to be concentration of the solution, the units of which must be defined. So the longer the path length, the higher concentration or absorptivity, the less light that's going to be allowed through, and the higher the absorptivity is going to be. Absorption is an indication of the amount of light that is removed from a beam following passage through a material. Another term, which is transmittance, is represented right here by capital T, and it's the ratio of the intensity of light that remains after passing through the material, which is going to be your lowercase l, to the input intensity, which is your LO. And that's what you're looking at here. LO is usually determined in a spectrophotometer by passing the light through a cuvette or a sample holder. The cuvette is just a tiny test tube. That's all it is. You're going to have your hands on it first thing in lab. And this contains a non-absorbing solvent. Okay, so it's determined by a spectrophotometer by passing light through a cuvette containing a non-absorbing solvent. So absorption is related to the intensity of light here. Okay, that's all we're talking about right here. Absorption is going to be related to the intensity of light, just as you see here. Now, if all the light passes through a material and none is absorbed, your A is going to equal 0 and your T will equal 1, like in this situation. Your percent transmittance, which is your percent T, is going to be equal to 100 T, or just simply 100. Now, this is the relationship between absorption and percent transmittance. Okay? So, absorptivity, or just A, as we're talking about it and looking at our formulas, is going to be a characteristic of a particular compound, and it's going to represent how much light is absorbed at a specific wavelength. If the concentration is known in units of molarity, then it is called the molar absorptivity. Now, molar absorptivity is the absorption for the molar concentration of a substance with a path length of 1 centimeter determined at a specific wavelength. So even for the same compound, absorptivity varies with wavelength. And without wavelength of light, absorptivity doesn't mean anything. A green material might absorb a photon at 617 nanometers and have very large value of absorptivity at this wavelength, but may allow a photon to pass at 448 nanometers, which it would pass completely, in which a 448 would be equivalent to 0. Now, since, according to Beer's law, the concentration of a sample is directly proportional to the amount of light it absorbs, we can determine the unknown concentration of a sample based on the amount of light that it absorbs at our given wavelength. So the first thing you're going to do is you'll scan through the visible spectrum of the dye to determine your lambda max. Then you're going to set your monochromator at the wavelength to determine the calibration curve of absorption versus concentration for the dye. And using this curve, determine an unknown concentration of that dye. Excuse me. So that is going to be really all that we have for our absorptivity or concentration, absorption versus concentration. If you have questions, make sure you're reaching out. Is a quick 9-minute video. And if you need to listen again, but I look forward to seeing you guys in class, and good luck.